solving exponential equations. There are several methods we can use to solve exponential equations. In previous courses, you learned to solve exponential equations by rewriting the expression with the same base and then equating the exponents. In this course, we will also learn that we can use logarithms to help us solve exponential equations. So if you had to solve 9 to the power of x equals 729, well, from previous courses you've learned that 9 to the power of x can be written as equal to 9 to the power of 3 because 9 to the power of 3 is 729. When the bases are the same, you can equate the exponents and therefore you can solve for x. X is equal to 3. Now here, 2 to the power of x plus 1 is 64. We will rewrite 64 as 2 to the power of 7. Now that the bases are the same, we can equate the exponents and say x plus 1 equals 7. So x equals 7 minus 1, which is 6. Or this one here, 5 to the power of 3x minus 2 equals 25. We're going to write 5 to the exponent 3x minus 2 is equal to 5 squared. Since the bases are the same, we can equate the exponents and say 3x minus 2 equals 2. 3x equals 2 plus 2, which is 4, and x equals 4 over 3. So we've learned this before. What would you do if you were asked then to solve the exponential equation 7 to the power of x equals 400? It is difficult to solve this like we did in the previous examples because we cannot rewrite 400 as 7 to a positive exponent, but which we could do in the previous examples we just did. So in this case, we have to use logarithms to help us solve. So we're going to find the take logarithms on both sides. So log to the base 10 of 7 to the power of x is log to the base 10 of 400. And we can bring the x down here. So x times log of 7 equals log of 400. And this helps us because we can isolate the x now, right? We can divide both sides by log of 7 to isolate the x. And we get x is equal to log of 400 divided by log of 7. We can use a calculator and it will give us the answer approximately 3.08. So this is how we would solve for a variable when we cannot use the exponent laws like we did in the previous examples. When trying to solve exponential equations, we're trying to isolate the term containing the variable on one side of the equation. Take the base 10 logarithm of each side of the equation, apply the power law of logarithms, and then solve for the unknown variable. So these are our 4 steps that we're going to use pretty much in all the questions. So let's try one. Solve each exponential equation, round your answers to the nearest hundredth. So these are examples where we cannot rewrite them in the same base and equate the exponents, okay? So we're going to use logarithms. So solve for x if 2 to the power of x equals 5. We're going to do logs on both sides. Log of 2 to the power of x equals log of 5. Bring the x here. X times log 2 equals log 5. You divide both sides by log 2 to isolate the x. And x is equal to log 5 divided by log 2, which is 2.32. So use your calculator for this answer. 5 to the power of t minus 1 equals 3.92. So we cannot rewrite this in base 5. So we're going to do logs on both sides. So log of 5 to the power of t minus 1 is equal to log of 3.92. This exponent can be brought down here. So it's t minus 1 times log of 5 equals log of 3.92. So t minus 1 is equal to log of 3.92 divided by log of 5 because we're dividing both sides by log 5. And then we can say t is 1 plus log of 3.92 divided by log of 5. At this point, we can just use our calculator to evaluate, and we get the t is equal to 1.85. So there we have the answer for solving the variable t. Let's try another one. 3 to the power of x plus 1 equals 4 to the power of x. We take logarithms on both sides. So log of 3 to the power of x plus 1 equals log of 4 to the power of x. And then we can bring this down here. So x plus 1 times log of 3. And we can bring this x also down here as x times log of 4. We can distribute the log 3 into the brackets here. So it becomes x times log 3 plus log 3, because 1 times log 3 is log 3, equals x times log 4. So the reason I'm doing that is I see there are two terms that have x in them, and I want to bring them together. So x times log 3 minus x times log 4, moving this here, is equal to negative log of 3. So x times log of 3 minus log of 4, put that in brackets, equals negative of log 3. And now I can isolate the x, right? I can divide both sides by log 3 minus log 4 to isolate the x. So I get x is equal to this, for which I can use my calculator, and I get the answer as 3.82. Okay. Two to the power of x plus 1 plus 2 to the power of x equals 192. So let's try to do this as take the logs on both sides. Log of 2 to the power of x plus 1 plus 2 to the power of x equals log of 192. And we can write this as log of 2 to the power of x times 2 plus 2 to the power of x equals log of 192. This is 2 to the power of x times 2 plus 1 equals log 192. So that's log of 3 times 2 to the power of x equals log of 192. We're trying to isolate the x. Going to change this, doing differently altogether. Try a different approach. 2 to the power of x times 2 to the power of 1 plus 2 to the power of x equals 192. And I'll factor out the 2 to the power of x and write this as 2 plus 1 equals 192. Or 2 to the power of x times 3 equals 192. I divide both sides by 3 and get 2 to the power of x equals 192 divided by 3, which is 64. And I can rewrite this as 2 to the power of x equals 2 to the power of 6, right? And you can equate the exponents. X equals 6. Okay. This one here, it's 3 to the power of 2x minus 3 to the power of x equals 12. This cannot be split like I did here, but I can create a new variable and say let a equals 3 to the power of x. Then if I square the a, that would be 3 to the power of x squared, which is 3 to the power of 2x. So therefore what happens is in this expression, I'm going to rewrite both of these terms. 3 to the power of 2x is going to be rewritten as a squared, which is what I have here. And 3 to the power of x is going to be rewritten as a. So my new expression now in terms of a and a squared is a squared minus a equals to 12. I did that is because it can help me see this as a quadratic equation in a. So a squared minus a minus 12 equals to 0. This might be factorable. This would be a minus 4 times a plus 3 equals to 12. And so therefore a is equal to 4 or a is equal to negative 3. Okay. And we're going to replace a with what we had defined a to be. A was, in our definition, a was 3 to the power of x, or 3 to the power of x equals 4, or 3 to the power of x equals negative 3. So we have two solutions. We're going to do that over here. If 3 to the power of x equals 4, and we take logarithms on both sides, log of 3 to the power of x equals log of 4. Bring the x here, x times log 3 equals log 4. Divide both sides by log 3 to isolate x. X equals log 4 divided by log 3. X equals 1.26. So we have one answer for x. There's also this one here. If 3 to the power of x equals negative 3, and we take logs on both sides, log of 3 to the power of x equals log of negative 3. This will actually not work because, you know, then when we find the log of a number, it should be positive. So it won't actually yield us any result we can use. So we bring the x down here. X times log 3 equals log of negative 3. We divide both sides by log 3. And if you take your calculator and try log of negative 3, it's going to say error. So then you would say there's no solution because you can't evaluate the logarithm of a negative number. Okay, so this is the only solution you have. We're going to look at some applications of exponential equations. We're going to recall some formulas we learned. Formulae we learned in the last course, the MCR3U course. The compound interest formula, A is equal to A0 times 1 plus I to the power of n, where AO is the initial amount, I is the interest rate, n is the number of compounding periods. So this is a general formula when something is growing and showing exponential growth at a rate of I%. And we also had this formula, A equals AO brackets 1 minus I to the power of n. And that was for relationships where there was exponential decay at the rate of I%. We also had two other formulae we learned, which is the half-life formula and the doubling formula. A equals AO times 0.5 to the power of t over n if you have a half-life question. And if you have a doubling question, use AO equals A is equal to AO times 2 to the power of t over n, where t in both cases represents the time and n represents the half-life in this case, and here the doubling time. So we have to know these formulae because we're going to use them depending on the kind of word problems we're given. So let's try a word problem. How long does it take $100 to double if it is invested in an account that pays 12% interest compounded monthly? So there's a lot of numbers here. $100, 12%, and that it's compounded monthly. So our final amount is our initial amount is $100, and we're asked to find, you know, how long it takes for it to double. So double means it becomes $200, right? And we are given that the interest rate is 12%, so it's 0.12. Because it's compound monthly, we're going to divide that by 12 to get I as 0.01. And our formula is A equals AO1 plus I to the power of n 200 equals 100 times 1.01 to the power of n. So in this case, we are solving for n, which will tell us how long it takes for $100 to become $200 at this rate of growth. I'm going to divide both sides by 100, right? And so we get 2 is equal to 1.01 to the power of n. So when you have an expression like this and you're solving for n, where n is the exponent, you can take logs on both sides. So log of 2 is log of 1.01 to the power of n. And we can bring this n down here. So log of 2 equals n times log of 1.01. We can divide both sides by log of 1.01 to isolate n and solve for it. And we get n is equal to log 2 divided by log of 1.01, which works out to about 69.66. So our answer is that n equals 69.66 compounding periods, right? So that is, in this case, it is compound monthly. So that is n equals 69.66 months. And we have to usually convert that to years. So n is equal to 69.66 divided by 12. So approximately 5.805 years. So it takes about 5.805 years for $100 to become $200 if it is compound monthly at a 12% rate. Next example, the number of ants in an anthill doubles every month. How long will it take for their population to grow to 9,600 if there are now 600 ants? So initial number of ants is 600. They grow to 9,600. Again, it's how long, so we're trying to find the value of n again. And it doubles every month. So we can use our doubling formula, which is A equals AO 2 to the power of t over n. And it doubles every month. So our, it's going to be 9,600 is equal to 600 t to the power of 2 to the power of t. 2 to the power of t equals 9,600 divided by 600. 2 to the power of t equals 16. 2 to the power of t equals 2 to the power of 4. T is equal to 4. Therefore, it will take 4 months. Now we can try some word problems.